So welcome to our last topic, and that's external flows from chapter 7. So external flows are flows over an object as opposed to flows in an object, which was our internal flow or our pipe or duct flow. What makes external flows more complicated usually is that you don't usually just have one flow direction. Usually your velocity components, there's at least two velocity components, and it could be changing in multiple directions. But the good news about it being more complicated is normally we have to go straight to experimental results, and that just means looking things up on graphs and then using those. So actually our external flow problems are a lot of times easier than our internal flow problems even. So let's first talk about Reynolds number. So if you remember Reynolds number just by definition is equal to some rho v some length over mu, okay, or v times some length over nu. L is some length, and v is some velocity. And what those two things are depends on what flow you're talking about. So for instance, in a pipe, where you have a diameter of a pipe, really anything round, usually you're going to talk about diameter is your length. So RE, and we use the subscript a lot of times to talk about what length scale we're going to use. So that's going to be rho V, where this is V, D over mu, or VD over nu. All right. So for a sphere or cylinder, again, those are round, so diameter, again, is going to be our characteristic length. So if this is our diameter, this could be a sphere or a cylinder, and our Reynolds number again is going to have a D subscript, rho. And for external flow, a lot of times we'll use U as our velocity. So rho UD over mu, or just UD over nu. Okay. Airfoil doesn't really have, it's not round, so we can't use diameter. What we use for airfoil for our characteristic length is the chord length. Normally. Okay, so we'd have RE sub C, rho, this again would be U, C over mu, or UC over nu. All right, so Reynolds number depends on the geometry, what's your characteristic length, and also on what's your characteristic velocity. For external flow, it's normally the incoming flow. Okay, so the outer flow before it gets to the object. Okay. Flat plate's a little bit different, and that's what we're going to really mainly focus on today. So if you have flow over flat plate, say it's a top of a building or the side of a building or top of a semi-truck or something like that, our Reynolds number, the characteristic length is actually going to be X. Reynolds number sub X, rho U X over mu, if this is U, or UX over nu. All right, so what that means and what makes this different is it's going to change. Reynolds number is going to change as we go along the plate. So in a pipe, Reynolds number was the same no matter what location you were at in the pipe. Okay, this is different. It's going to be changing, and that means we're going to call that a local Reynolds number. So you could find the Reynolds number at x equals 1, or Reynolds number at x equals L, or whatever. Okay, so Reynolds number, local Reynolds number means it changes over the length of the plate. Okay, and all kinds of different Reynolds numbers for various shapes, and sometimes if you're doing the experiments yourself, you have to figure out what length scale you think is the most important for whatever object you're testing, and then create a Reynolds number based on that. And we use Reynolds numbers because, again, it's a major non-dimensional parameter, so if you want to plot some experimental results, usually you're going to do it versus Reynolds number. Okay, so here is Reynolds number, flow over flat plate. So when you get to the very beginning of the plate, and let's make this pointed so we don't have any like strange flow due to that front of that plate. So when you first get to the beginning of the plate here, if this is X, then X equals 0, and the Reynolds number at x equals 0 is 0, right? So you're going to start out at a low Reynolds number, and it's going to increase as you go on here. Well, low Reynolds number is laminar. So for a flat plate flow at the entrance here, you're going to have laminar flow. Unless you trip it to turbulent, it's going to be laminar. Okay, so you're going to get a boundary layer that looks something like that with a velocity profile, something like this, nice and smooth. Okay, but then what happens as you go along this plate is your Reynolds number is going to increase, and then you're going to start to get some transition. So you get a little bit of wiggles here and there. So this would be your transition region. And what I'm drawing is the boundary layer. Okay, and then eventually it's not going to just be unstable in the transition region, but it's going to go fully turbulent. And when it does that, your boundary layer actually gets quite a bit thicker. Okay, and if you look at a streamline going through the middle of this is your boundary layer edge again. If you look at a streamline, nice and smooth in the laminar part, and then it'll get some wiggles here and there. And then it's going to go turbulent. So there's your turbulent. This is your streamline. Your streak line. So that's as if you're putting like dye in the flow. That's what's going to happen to it. And here it actually would just disappear because it's just mixing with the flow around it. So Reynolds number increases as you go along the plate. Okay, so always going to start laminar. Unless you try to make it turbulent on purpose, it's going to start laminar, and eventually, if the plate's long enough, it'll go to turbulent. So it's different from internal flow, where it was all laminar or turbulent along the whole length. Okay, so critical Reynolds number meaning where it's going to transition from laminar to turbulent. For a flat plate, that is approximately 5 times 10 to the 5th. So that's what we're going to use as our critical Reynolds number. Okay, one of the most common mistakes that people make when they get to external flow is to use 2300 as the critical Reynolds number for flat plate, but it's not 2300. That was for pipe flow. So remember that. It's not 2300. Do not use 2300. And that's an approximation. This 5 times 10 to the 5th is an approximation. If it's super, super smooth, you could actually get up to like 3 million and still have it laminar. So again, big approximation here. But if the Reynolds number is less than approximately 5 times 10 to the 5th, it's going to be laminar. And otherwise, it'll be turbulent. Okay, so that's what the critical Reynolds number means. It's about where it's going to switch. Okay, so remember that each geometry is going to have its own critical Reynolds number. Okay, so that's why pipe flow had a critical Reynolds number of 2300. Flow over flat plate, 5 times 10 to the 5th, so they're going to be different. Most geometries, we don't even use critical Reynolds number. We aren't really concerned. We just go straight to experimentation, and it is what it is. We don't care whether it's laminar or turbulent. But for flow over flat plate and pipe flow, we do use the critical Reynolds number. Okay, so let's talk about what is some differences in internal flow versus external flow as far as what we're trying to find. So internal flow, so pipe flow again, there were a bunch of things that we would calculate for, solve for. Delta P maybe, Q, D, maybe our losses, HFs and HMs, maybe our pump or turbine power, HS or W dot. And in order to do that, in order to find those values, what we did was use the energy equation. For external flow, we're not trying to find those same kind of things at all. What we're usually trying to find are forces. And a lot of times that's lift or drag. Lift and or drag. Not always. If you remember from the lab, we were trying to find the frequency of vortex shedding. Okay, so that's another thing you could be finding. But a lot of times for flow over an object, drag is usually, for wings you also find lift, but most of the time what we're looking for is drag. Okay, we want to make things aerodynamic sometimes. So if we have forces in external flow, let's talk about what lift and drag are. If you have an incoming velocity, or this wing is actually moving into the still air, that velocity u, drag is the force that's going in the same direction as the flow. And then lift is what is perpendicular to that. Okay. In the end, you would get a resultant for this particular case like that. Okay. Drag is going to be due to two possibilities. Okay. One are pressure forces, and the other shear forces. Okay, so pressure forces, if you remember, that's the perpendicular force due to pressure, and shear is the parallel force. So shear is like friction. Okay, so looking at pressure drag, if you get a non-uniform pressure on the surface of a body, you'll get a net force. Okay, so if this is your flow coming in, you're going to have the highest pressure here in the front, lowest pressure here on the sides probably. So you will get a pressure distribution maybe like that. And if you have your biggest pressure on the front, you will end up with a net force, a net drag force. Okay, shear stress drag is the friction drag. So it's the forces going this way. So when the fluid, back here you might get going the other way, when the fluid is rubbing on the surface, it's going to create a force, and those are your shear forces. Okay, and different objects will have different amounts of pressure forces or shear forces. Usually one or the other is dominant. Okay, so for instance, if you compare these two flat plates, one of them is in line with the flow, like this one, and if I draw some streamlines over it, it's going to look something like this. Your main forces here are, your main drag is mainly due to shear, because most of your velocities are going parallel to that surface. Okay. If you, on the other hand, have it oriented perpendicular to the flow, then this is what your streamlines look like. Maybe they curl in here, something like this. You get some separation with some vortices going on. In this case, the drag is mainly due to pressure. So you're going to get a much higher pressure on the front because that plate is having to turn that fluid than you have in the back, and you have kind of a void in the back where those vortices are, where that separation is. Oops. Which is also going to cause drag. So you're going to get a much higher drag in this case. Okay, so our solution strategy on these problems. If possible, you could solve the Navier-Stokes equations. Not usually possible. We do have laminar flow over a flat plate solution. We're not going to go through it. It's pretty complicated actually, but we do have that solution because somebody has done that for us before. But other than that, it won't be possible to do the Navier-Stokes equations. Another option is to use numerical analysis, or CFD, and that's very nice to use, not always perfectly accurate. Another thing you can use is boundary layer analysis. So you can do something like we do with the flat plates and do a more complicated kind of analysis close into the surface, and then use Bernoulli's estimation where there aren't any losses. It's called inviscid flow for the outer flow. A lot of times you do that for wing flow if you were taking an aerodynamics course. And finally, use experiments, and we do that a lot in this when you're doing external flow. So that's what all the car companies will put their cars in the wind tunnels and so forth, so that they can figure out the aerodynamics of their cars. So stop here and do quiz questions 1 and 2.